Alright, so today in pre-calculus I learned about Stewart's theorem. Yay! What a theorem. It takes a bunch of lengths in a triangle and this line and then puts them together in this strange formula that can be memorized more easily by saying dad plus man equals BMB plus CNC. How enlightening. So, I tried for like an hour trying to prove this using the law of sines because I thought that was how you would prove this thing, but it turns out no, it was the law of cosine, and when I used that it took me like a minute to solve this. So to express my frustration, here's just a quick demonstration of how it goes. So using the law of cosine, and so how do we prove this I don't know, equation, or this identity, or I guess this equation about all these different lengths of a triangle? Well, let's just, using trigonometric identities or trigonometric laws, let's try to find a way to bring them all together. So using law of cosine, what are some special angles in this triangle that can only be found because you added that one line? Well, hint hint, maybe these two angles. They're supplementary, you know? And this angle branches off into all this stuff, and this angle just branches off into all this stuff. Well, what if we use the law of cosines right there and right there? Let's try it. Let's just call this angle theta. Let's call this angle phi, or phi. Yeah. You know, we could we call them different variables just for now. So using the law of cosine, let's just do it for theta. So we could just say law of cosine, the opposite side, right? C squared equals d squared plus m squared minus 2dm, yeah, times cosine of theta. Now what? Well, what if we want to just get the cosine of theta just completely by itself, just isolated on one side? There is another way to rewrite the cosine of theta, so that the law of cosines, just so you get cosine of theta just completely by itself on one side. You can just add this. You can just move it to the other side. Move the c squared to the other side. Divide both sides by 2dm. Just do some algebra. Isolate it. So let's just rewrite this real quick as cosine of theta equals d squared plus m squared minus c squared all over 2dm. Do the math. It checks out. So, if you can see that. Now, we can do that with the other thing too. Hang on, let me just zoom in a little bit more. Now, there we go. So, now let's do that with little phi over here. So, sorry if you can't see it. Let's just use this law of cosine. So what I mean by that is just cosine of phi equals, now what? It's d squared, you can see that, d squared plus n squared. So write that, d squared plus n squared minus b squared over 2dn. There we go. Pardon my neat handwriting. So, but the thing is, with these two cosines, we know something special about these because theta plus phi, they add up. They're supplementary. So one thing about supplementary cosines is that if you got cosine of a, alpha, and you got cosine of 180 minus alpha, there is an identity that shows, that's kind of, that you can try to prove if you want, if you don't know, that that this cosine of 180 minus alpha is just equal to minus cosine of alpha. Yeah, that's it. So since phi is 180 minus theta, this is actually just minus cosine of theta in a way, right? There we go. So we can just substitute what we already have for cosine of theta into this. So let's just do that. So minus cosine of theta, this. So we got d squared plus m squared minus c squared all over 2dm, and this equals d squared plus n squared minus b squared all over 2dn. Now, some simplifications. The two d's cancel each other out. Be having none of that around here, and then we can just to get rid of this. To get rid of the denominators, we can multiply both sides by mn. So mn, and multiply this side by mn2. So then the m's cancel out here, so you just multiply everything by n. And here the n's cancel out, so you multiply everything by m. You got m's and n's. Yeah. So let's just do that. And also, while we're at it, we can let's just distribute this negative into all these terms on this side. So in the end, we end up with minus d squared times n, right? Minus m squared times n, and then minus c squared, so it's a positive c squared, plus c squared times n, and then all that equals d squared times m plus n squared times m minus b squared times m. M and n. So they sound very similar on a microphone. So, and now we got all these negatives and positive terms and all this whatnots, right? So let's just I just want to move all the negatives to one side, make them positive, move all the positives, let the positives stay where they are. So let's just do that. Let's just take all these negatives and just switch them. So let's just move this to that side, so we get positive b squared times m. So we got here, we got b squared times m plus c squared times n equals then d squared times m plus, oh, I'm getting confused here, n squared times m plus d squared times n plus m squared times n. Now, hold on a minute. Hold on just a second. There's some things here that are similar. We have a d squared and then a d squared, right? And then here we have an m and an n, and here we have also an m and an n. N and m's, or m and n's. So let's just try to group this together. So with the d squareds, we can factor these out just to get a d squared times m plus n, right? And then here, these both have an n and an m. They have extras, but we know that they both have an m and an n. So let's just factor those out too. So an n and an m, right? Then in the end, we're left with an n and an m. And since these have the same things, right, we can factor yet again these two terms. So just take these out, then we get m plus n, right, these are the same, times d squared plus n m, or mn, whatever. And the thing is, we know something about m plus n. M plus n, that's just a, right? It's just the addition to this one length. So we can just rewrite this as a, right? And then rewrite the rest as d squared plus mn, right? If you want to get exact. And then rewrite the rest right down here as b squared times m plus c squared times n. So we've basically reached the exact same conclusion as up here, right? We got the dad, we got the man, we got the little BMB and the CNC, and we have a very interesting way of looking at lengths of a triangle. And we are done.